to start out with something that we've already talked about back when we talked about the average rate of change of a function. So the question here is, say I have a generic function drawn, and I'd like to find the slope of that function. Now, of course, the slope varies depending on where I am on the graph. So I can't tell you the slope of this function across its whole domain is, say, some number, because this function is not linear, right? A linear function is the only type of function that has a constant slope. However, well, if I can't find the precise slope across the whole domain, what if I start by, say, finding an estimate? So say I pick a region. So I pick a value of x. We'll call this, say, a. And then I say, okay, well, let me go another distance here, and we'll call that h, to my second x value, so that would then be a plus h. And then let me connect those 2 points with a line. Okay, so roughly, that line looks something like that. Okay, so by the way, that line is called a secant line. And so what I can do is, now I'm looking at a line through the 2 points. I guess this point would be a comma f of a, and this one would be a plus h, f of a plus h. So now that I have a line, well, I can find the slope of that line just by looking at the rise over the run. In other words, the y2 minus the y1 over the x2 minus the x1. So here's y2 minus y1. And then my x's, x2 and x1. Those cancel. So I have f of a plus h minus f of a over h. So this formula has a special name. So this formula we call the difference quotient. Okay, so what information does this give me about the graph of a function? This gives me the slope of the secant line, okay, from x equals a to x equals a plus h. So that would be the slope of the red line here. So as you can see, that is not exactly the slope of the function, but depending on how far apart the points a and a plus h are, I may get a pretty accurate estimate of the slope of the function, or I guess I may not. But in any case, this is an approximation of the slope of the function in that region then. So that's the information that this formula gives me. Okay, so maybe before I start this example, I'm kind of interested in looking at one more thing. So what if I kind of continue the process here? Let me clean this up a little bit. I'm going to use the same graph. Actually, let me leave that apart. So maybe even, let me delete this. Okay, so what I'm interested in now is, all right, well, the difference quotient is nice enough. That gives me an estimate of the slope of the function. But if you look at the picture here, I mean, the closer the second point is to the first point, the more and more accurate an estimate I'm going to get of the slope of the function at the point A itself. Okay, so what am I saying? As the second point moves closer to the first, I get a more and more accurate estimate of the slope of the function at that single value x equals a, which is what I'm really interested in. So what we do here is we say, okay, so if I'm taking the second point and moving it closer and closer and closer to the first point, what is happening to the value of h? So as the second point moves in on the first point, isn't h getting close to 0? In other words, the distance between the 2 points is going to 0. So what if I write this out mathematically then? And I say, okay, so what if I find the limit as h goes to 0 then of this difference quotient? So actually, once I evaluate that limit as h goes to 0, I'm saying now the second point has moved all the way over to the first point. The h has become 0. Okay, so now what I've actually found is the slope of this line through just the point A. Okay, so that line also has a special name. That one's called the tangent line. Okay, so this guy is actually a very important formula. This guy is the definition of the derivative. So let me get rid of this. Okay, so this guy, we call it f prime of a. And we'll write out, so I'll move it up here, I guess. This guy is called the limit definition of the derivative. So like I said, this is something you're going to spend a fair amount of time in calculus looking at. And so we would read that the limit definition of the derivative is f prime of a is the limit as h goes to 0 of the difference quotient. And so what this guy gives me the slope of the tangent line. Okay, so that's the line that goes through the single point x equals a here. So in other words, what I've actually found then is the instantaneous slope of the function at the single value x equals a. Okay, so I have really two different formulas. So there's the difference quotient, and what does that one give me? That gives me the approximate slope of the function. Notice for the difference quotient, I have to have 2 points. The secant line goes through 2 points. Versus the derivative, that guy gives me the instantaneous slope, so the precise slope of the function at a single value. So to use that definition, I just need one number. The tangent line goes through only 1 point. Okay, so I have tangent line, and then I have secant line. So then, let's go back down here. And look at some of these examples. Okay, so I guess I was going to go ahead and graph this function. Okay, so f of x is x squared plus 1. Let me graph that. Okay, so I've got 0, 1, got 1, 2, 2, 5. Okay, and that guy's symmetric over the y-axis. Parabola would look something like that. Okay, so there's the function. So the first question says, find the difference quotient. Okay, so let's see where that one is. So that's this one here. So that's my general formula. Okay, so what I have to do is I have to apply that formula to this specific function. Okay, so my template, the denominator always has the h in it. The numerator, I have to fill in these two quantities, f of a plus h and f of a. So those would, of course, depend on the specific function. Okay, so for my function, if I plug a plus h in, I get a plus h squared minus 1, plus 1. Okay, so that's what goes here. Okay, so that guy, this is the f of a plus h. That's this piece. Okay, then I have a minus, and then I have to put f of a. Well, that's really easy. If I plug a in my function, isn't that just a squared plus 1? Okay. Then I just need to simplify my difference quotient. Okay, so then again, this is the f of a. Just doing the arithmetic now. So I have to do a FOIL. So that's a squared plus 2ah plus h squared plus 1. A plus h squared is a plus h times a plus h. A squared 2ah's plus an h squared, right? Distribute my negative. And then usually I get a lot of cancellation with these. So my a squareds can go, and my 1's go. So I've got 2ah's plus an h squared over h. Okay, now something you'll notice with these difference quotient problems is that this h in the bottom always cancels. Okay, so I know if I haven't canceled that h, I'm not done with the problem or I've made a mistake. You see how here I can actually factor h out of the numerator? So indeed, my h cancels, and so I end up with 2a plus h, and that's my difference quotient. Okay, so then maybe I should write some sort of an explanation for what this is. That's the difference quotient. So this is the slope of the secant line to the particular function x squared plus 1 from x equals a to x equals a plus h. So again, that's the approximate slope of the function itself. Okay, so then what am I asked to find next? So now the next question says, find the slope of the secant line from x equals 1 to x equals 3. So I guess another way I could phrase this question would be I could say, find the approximate slope of the function from x equals 1 to x equals 3. Okay, so, the good news is I already found this formula here. This gives me the slope of the secant line from a to a plus h. So all I have to do is figure out what I need to plug in. So look, from x equals a. So a is 1. 3, okay. So what is h? So h is the distance between the two values. So the distance between 1 and 3 is 2. So the h would be 2. So now I'm just going to take those and I'm going to plug those in my difference quotient formula. So the difference quotient would be 2 times a plus h. Oops, and my h is 2. So 4. Okay, so this is the slope of the secant line from 1 to 3. Okay, now I can look at the picture. Now I was looking at this, maybe I need to extend my graph a little bit then. Let's see, if I plug in 3 squared is 9 plus 1 is 10. It's going to fit 2, 4, 6, 8, 10. It'll be here. I'm trying to draw that reasonably. Parabola, looks like so. Okay, so I found here, let's see, the slope of the secant line from 1, it's here, to 3, that's here. Okay, so it looks something like that. That point and that point. So what did we find that slope to be? 4. Okay, let me look and see. So 1, 2, 3, 4, right 1, 1, 2, 3, 4, right 1. Oh, look at that. So indeed, that line has a slope of 4. And then you can see, okay, so that looks like it gives me a reasonable estimate of the slope of the function itself in that region. That secant line is pretty close to the function. Okay, so what else can we do? So now we have find the slope of the tangent line at x equals -2. So remember when I see that, I go, okay, so I need the limit definition of the derivative. That's the one that gives me the slope of the tangent line. Okay, but the good news is, actually, the limit definition of the derivative, it's just the limit as h goes to 0 of the difference quotient. So actually, for this function, I already found the difference quotient. Where is that? It's right here. Okay. So I already know that information. This is a very easy limit to evaluate. So if I plug 0 in, don't I just get 2a? Okay, so what is this? This is the slope of the tangent line at x equals a. Okay, or the instantaneous slope of the function itself. So I could say that's actually the slope of the function itself at x equals a. Okay, so now this problem says specifically at x equals -2. So that means I need to plug in -2 to my derivative. Okay, so the slope of the tangent line specifically at x equals -2 is 4. Okay, or -4. Oops. Okay, if I look back at the graph, let's see, so here's -2. So we're saying, okay, if I draw that tangent line, its slope should be -4. Well, seems reasonable. Let's see what the next part is. Next part says, okay, now actually find the equation of the tangent line at x equals -2. So I've already found the slope, right? So to find the equation, all I have to do is say, okay, well, I'm looking for the equation of a line. There's the equation of a line in slope-intercept form. So I've actually already found my slope. All I have to do is get the b. Okay, so in order to get the b, I have to plug in the point of interest. So the x is -2. Well, what is the matching y? So let's see, the function is x squared plus 1 would be 5, right? Okay, so the point of interest is -2, 5. So then I'm going to plug those values in for the y and the x and solve for b. And then I'll write the equation. And then I'll look at the graph and I'll see if that looks correct. So I'm going to graph a line with a y-intercept of -3 and a slope of -4. Can even clean some of this up. Okay, we're done with all this. Okay. Alrighty. So then let me see. I don't remember what it was now. It was -4x minus 3. Okay, so the y-intercept is -3. Slope is -4. So I'd go 1, 2, 3, 4, left 1. 1, 2, 3, 4, left 1. Okay, and then let me draw a line. Okay, that'll do. Okay, didn't do a great job drawing that, but like so. Okay, so indeed, that's the line tangent to the graph here at x equals -2. here's another one. Find the equation of the tangent line to the function f of x is square root of x plus 6 at x equals 3. Okay, I guess I'll start by graphing the function. It's a root function shifted left 6. Need to move this again, huh? Okay, let me try again. So I'm going to have negative 6, 0. Let's see, negative 5, be 1. Let's see, negative 2, 2. What's the next one? 3, 3. There's my root function. Okay, so I have to go through a series of steps. So the first thing I'll have to find will be the difference quotient. So my general formula looks like so. So for this function, let's see, I'll have root of a plus h plus 6 minus root of a plus 6 over h. So then I have to simplify that. Remember, I have to simplify until I'm able to cancel the h in the denominator. So what if I try multiplying by the conjugate? So I keep the same expression, but with the opposite sign in the middle. Okay, and then I do a FOIL in the numerator. So I'm squaring that root. Okay, look, I get a positive and a negative. Same root cancels, right? So then I'm just left with negative a plus 6. Oops, and then don't forget, in the denominator here, I'm multiplying straight across. So don't forget the second factor here. Okay, so I'm just left with an h in the numerator. So actually my h will cancel with my h. And so I'll just have a 1 over root a plus h plus 6 plus root a plus 6. So that's my difference quotient. Okay, so remember what information that gives me. This gives me the slope of the secant line to this root function. From a to a plus h. Okay, so then I have to continue because what I wanted was the equation of the tangent line, not the secant line. So the next thing I need, step 2, will be to find the derivative. So that's the limit as h goes to 0 of the difference quotient that I already found. Okay, so now I go ahead and I plug in 0 for h. So then I've got a root a plus 6 plus a root a plus 6. 2 roots of a plus 6. So this is f prime of a. So this is the derivative, or in other words, the slope of the tangent line at x equals a. Okay, now I have to plug in my number. So I have to get f prime of 3. Okay, so this is the slope of the tangent line at x equals 3. All right, so now that we know the slope of that tangent line is 1/6, all that's left to do is actually write the equation of the tangent line. So that's our y equals mx plus b. And then we know the slope is 1/6. So then all that's left to do is get b. And so remember, to do that, I have to plug in the point of interest. So let's see, what was the x value? The x was 3. Then I have to look back at the function. So f of 3 is square root of 6 plus 3, so root of 9, 3. Okay, so I'm going to plug the x and the y in and solve for b. So what is b? 5/2? 2.5? So the equation of the tangent line would be like so. Okay, and then I can at least do an estimate here. If I look back at the graph, so what is it, 1/6? It's plus 5/2, so let's see, it'd be at about 2.5. It's here-ish. Okay, and then the slope is 1/6. So down 1, right 1, 2, 3, 4, 5, 6. More like so. And then up 1, 1, 2, 3, 4, 5, somewhere over here-ish. Okay, and then I'll try to connect those to see my tangent line. Okay, and so you can see that tangent line goes through the point of interest, 3, 3, and looks like it's tangent to the graph at that point. So that looks pretty good. Let's look at one more. Find the equation of the tangent line to the rational function f of x is 2 over x minus 3 at x equals 1. Okay, so again, the first step is finding the difference quotient. So the general formula for that looks like so. And then let me plug in the a plus h. So that'll be 2 over a plus h minus 3. And then plug in the a, 2 over a minus 3. Okay, now I'm going to use that trick where I'm going to multiply the whole top and bottom by the LCD. Okay, so LCD. So that I'd need, let's see, a factor a plus h minus 3 and a factor a minus 3. Okay, then I distribute. So when I distribute to the first fraction, okay, what's going to happen there is the a plus h minus 3 is going to cancel. So what I'll be left with is the 2 and then the a minus 3 from over here. Okay? Then when I distribute to the second fraction, the a minus 3 is going to cancel. So I'll be left with the 2 and the a plus h minus 3 from here. Okay, and then my denominator, I just multiply straight across. So it's h times a plus h minus 3 times a minus 3. Okay, let me distribute in the numerator. Denominator is already factored, so I'll leave that as it is. Okay, so what do I have? 2 a's cancel, 6's cancel. So I'm just left with the negative 2h in the numerator. H's cancel. So I have negative 2 over a plus h minus 3, a minus 3. And there's my difference quotient. Okay, so thinking again about what information this gives me the slope of the secant line. Okay, so this is the approximate slope of the function. Okay, so this is the slope of the secant line, the line through 2 points, x equals a and x equals a plus h. Okay, so what was I looking for? Well, remember here, I'm looking for the equation of the tangent lines. I have to continue. Not looking for the secant line, I'm looking for the tangent line. So step 2, again, is find the derivative. Okay, so that's f prime of a is the limit as h goes to 0 of the difference quotient. Okay, so f prime of a is the limit as h goes to 0 of the difference quotient that I just found. So I've already done all the algebra. Okay, so if I go ahead and I evaluate, then all I'm going to be left with is negative 2 and then a minus 3 times a minus 3. So a minus 3 quantity squared. So this is my derivative. So this guy gives me the slope of the tangent line at x equals a. So now I'm going to plug in the x value of interest. So let's see what the x value of interest was. It was x equals 1. Okay, so for step 3, I'm going to say, what is f prime of 1? So that's negative 2 over over 1 minus 3 squared. Negative a half. Okay, so what is this? This is the slope of the tangent line, specifically at the value x equals 1. So now all that's left to do is step 4, which is actually write the equation of the tangent line. And so to do that, remember I have to get the b. Because I already know my y equals mx plus b, all I need to do is figure out that b value. And so I have to, again, plug in the point. Okay, so let's see. The x value was 1. Let's find f of 1. Okay, here's the function. 2 over x minus 3. It's like negative 1. Okay, so the y is negative 1. X is a half. Let me see. That y is negative 1. The slope is negative a half. The x is 1. Solving for b. Add the 1/2. Looks like b is negative a half. Okay, so therefore, the equation of that tangent line would be negative a half x minus a half.